Okay, so we have learned that reaction rates generally increase when the reactant concentration increases, right? In a reversible reaction, the reaction can proceed in the forward direction and in the reverse direction. So if we start out with just reactants, the reactant concentrations are high, the rate of the forward reaction will be fast. And then as the reactant concentrations drop, the rate will drop, depending on what order it is, but typically. Initially, there's no product, and so the reverse reaction can't happen. But as the forward reaction proceeds, we get to some product formed, and so now this concentration increases, and that will increase the rate of the reverse reaction. Does that make sense? So we can look at it in a bunch of pictures here. Yeah.
Okay, so I feel like this equilibrium in a reaction, isn't it something that occurs all the time, even in nature?
Yes.
Because, okay.
Yes, the concept of dynamic equilibrium is everywhere. Yeah. We just don't necessarily notice it.
It happens so fast that at any point when you measure it, it's still going to be equal to...
So what we'll see is that the concentration, at equilibrium, the concentrations of the reactants and the concentrations of the products are not changing, and yet the reaction is proceeding in both directions. It's like a busy highway where people are going south and people are going north. And if you counted the number of people down there and you counted the number of people up here, it might be the same number of people, but it's not the same people. And so there's all this activity, and yet when you back up and look at the overall picture, nothing seems to be changing. It's really kind of weird. Did you have a question?
I think the highway thing.
Oh, okay. So let me try to explain this graph to you, or this figure. Up here we have some clocks, and so this is representing time passing. Here, this is the reaction we're looking at, H2 plus I2 making 2HI. So initially, when things begin, all we have is the hydrogen and the iodine. And so if we look at this graph, we see that the concentration of hydrogen is this value, the concentration of iodine is this value, and there is no product, HI. Okay? As time goes on, some of the reactants react, and we start to get some HI forming. So the HI concentration is going up, and the H2 and I2 concentrations are going down as that forward reaction proceeds. You with me? And it will continue, and we're getting more product, and then after a while, the amounts of reactant and product are the same now. Because what's happened is the product concentration has increased to a point, and the reactant concentrations have decreased to a point where the forward and the reverse reactions are occurring at the same rate. And so then the concentrations remain constant. Yes?
So when we are performing experiments and we get a kind of less than ideal percent yield, it's not entirely our fault, it's just that.
Yeah, so equilibrium can be the reason for a less than ideal percent yield, because some reactions do not go very far to completion. And so you can calculate your theoretical yield, but if the equilibrium constant isn't huge, then you might only get 75% of it, and that might be the best you can get.
But by using catalysts or other agents?
There are ways that we can make it go farther, and by understanding how it works, that allows us to make it do what we want it to do.
Right.
Yeah.
Now, once they cross and they hit that dotted line, where the reverse reaction is the same, can they ever cross back again or no?
So if we get to this point and we don't disturb things, they will stay. Now, if you take something out, put something in, change the temperature, or do some other stuff to it, you'll disrupt the equilibrium, and then it will shift in a way that will try to restore the previous equilibrium.
So that's like sometimes like when we're stirring something, like you only want to stir it like right at the beginning, and then kind of like with this experiment we're going to do today, it's like it says like to stir it for a while and then just leave it. 'Cause
Right.
if you touch it again, something will happen to it. Or
We don't want how much you're swirling it to affect how long the reaction takes. It needs to get mixed, but then, and you could do a whole study on that. Well, if I set it on the stir plate with a stir bar and I have it this revolution, or if I'm just kind of shaking it occasionally, how does that affect how long it took for the reaction to occur? And so some of those things in the experiment we know could mess up your results, and so we try to take them out. A good experiment is going to have all of its variables controlled, and so we don't want the rate of stirring to affect your results. So any questions about this figure? So we're talking about a dynamic equilibrium because we have a forward reaction and a reverse reaction happening. That's why it's dynamic. It's not static where nothing's moving. It's dynamic. Things are changing, but the forward reaction and the reverse reaction are happening at the same rate. Trying to think of a good analogy, and my analogy maker is not functioning really well. Let's say you had two kids and one of those double sinks in the kitchen, and there's water in both sinks. And the kid on the left has a cup, and he's dumping water into the right sink, and the kid on the right has a cup, and he's dumping water into the left sink, right? If they're dumping water into the other kid's sink at the same rate, is the level of the water going to change? No. If one kid is faster than the other, then the level will change because the water in his sink will go down and the water in the other kid's sink will go up. But here we have things occurring at the same rate, so overall there's no change. What's important to recognize is that the concentrations of reactants and products are not changing, but that does not mean that they are equal. Okay? It just means that they are staying the same. You could have one that is a very, very low concentration and the other's really high, but they're staying where they are. And so that's what's happening at equilibrium. The relative concentrations are going to depend on the value of that equilibrium constant. There are some, if you have kind of a very middle equilibrium constant, like around 1, you might have equal concentrations of reactant and product. But that's because of the equilibrium constant. It's not a characteristic of a dynamic equilibrium. So this is an analogy. And now it's labeled country A and country B. I don't know if the publisher or something got in trouble or what, but it used to be called Narnia and Middle Earth. And I just thought that was more fun. So here's Narnia and Middle Earth. So here we have Middle Earth is very, very sparsely populated, and there's a whole bunch of people in Narnia. And so what's going to happen? Where are the people going to go? It's really crowded over here, and they see that there's all this land available. You can have space to spread out. You can have a bigger farm. And so people are going to move from Narnia to Middle Earth, right? And so that will proceed until we've got an equilibrium situation going on. And so it could happen that now we have equal population density in the two countries. We still have people moving from Narnia to Middle Earth, and people moving from Middle Earth to Narnia because, you know, maybe you married somebody whose family lives in the other country and you move over there, or you're just a dissatisfied person and the grass is always greener on the other side of the country line or something. There are lots of reasons for moving to different places. But at equilibrium, we have population moving equally in both directions. And so the population of Narnia is going to remain the same over time, and the population of Middle Earth is going to be the same. But it's not always going to have the same people in it. Does that make sense? Anybody have any questions about that? Yeah.
Is dynamic equilibrium, does it only happen in gas phase reactions?
No, it can happen in other than gas phase reactions.
Okay.
It's easy to talk about in a gas phase reaction,
Right.
but
It's
it
like
can
number of
happen in
moles,
any
like this.
combination. Yeah,
Number of moles and like pressure and SU
Right.
play.
yeah. Now, can you think of a reason why maybe the population of Middle Earth would be much larger than that of Narnia? Well, but population density wouldn't depend on how big it is. Well, what if they had really generous social services here, right? And the soil was really rich, and yeah, all those things that people think they want. You know, the economy was really booming, right? And so that might cause people to prefer living in Middle Earth, and the population here might be larger than the population over there. Maybe there's a drought over here, or the soil got poisoned by salt, or there's, you know, coronavirus or something, right? So just pulling in current events, right? Yeah, you know, or maybe some orcs are on the rampage or something, you know. But you can yeah. But you can see why population could vary, right? I mean, there's a reason. Have you ever driven through Nevada?
Yes.
There's a reason that you can drive for hours and not see a person other than on the freeway trying to get out of there, right? It's a desert, right? There's not a lot of water. There's just not a lot of opportunities. And then you go to other places, and there's just like people everywhere. Was it a more desirable place to live? Did you have a question?
Yeah, so there could be like more people in one country but still equal movement?
Yes. Yep. So you could have a very high concentration of people, high population density here, a low population density here, and they could still be at equilibrium. You're still going to have some people moving from one side to the other, but the populations are going to be constant. Okay? Okay, so let's see if we can do this one. Which statement does not generally apply to a chemical reaction in dynamic equilibrium? The rates of the forward and reverse reactions are equal. The concentrations of the reactants and products are constant. The concentrations of the reactants and products are equal. C. That is not true, right? The concentrations of reactants and products are not going to be equal, except in very rare situations. Okay, so what is this equilibrium constant? And wait a minute, this is a new section.